So welcome everybody to the last seminar of our spring series, actually, but we'll continue over the summer. And so today we have Isaac Legred from Caltech, where he's a graduate student to give us a talk on the effect of correlations in models of the nuclear equation of state on neutron star inference. So please, Isaac, go ahead.
Thank you so much. Yeah, I'm Isaac. I'm a graduate student at Caltech, and today I'm going to be kind of talking about how correlations in models of the nuclear equation of state can impact neutron star inference, so the inferred properties of neutron stars and vice versa. This is based on a recent paper that wrote along with Katerina Hatzianu, Reed Essick, and Phil Landry. So let's get into it. To start, this is going to be just sort of a very basic overview that I'm sure is familiar to many of you here, but why do we study neutron stars? Well, there's two very interesting properties of neutron stars, in my opinion, and that's that general relativity fully matters inside of neutron stars. So the details of general relativity matter, and the details of the behavior of nuclear matter are uncertain because they're higher than sort of the densities that we can probe on Earth in terrestrial experiments. And so these two facts kind of combine and give us a laboratory to study nuclear physics along with general relativity. And one of the lessons that we can kind of learn from this is that both of these are relevant to get the maximum amount of information that we can get. They're sort of codependent. To give an example of this, why do we want to infer the equation of state? Most of my time is spent in astrophysics, and so one of my main priorities is astrophysical phenomena. And so why study the equation of state in the first place? The answer is that there are relationships between the microphysics of the equation of state and the macrophysics that we see with neutron stars, the details of the astrophysical phenomena. So for example, from the equation of state, we know we can compute neutron star properties using the equations of neutron star structure. And then given neutron star properties, we can infer the equation of state by just examining what properties are and if they're consistent with the equation of state. So to kind of give an example, the first idea of neutron stars, the hypothesis came out as soon as the neutron star was discovered, essentially, like the next year by Bed and Zwicky. The idea was a star made of degenerate neutrons could be extremely dense, perhaps the densest thing in the universe before collapse to a black hole, although the idea of black holes wasn't really established at that point. But we now know that this equation of state that is consistent with degenerate neutron matter, non-relativistically degenerate neutron matter, is not consistent with observations of pulsars. So this is, for example, a recent mass measurement of this J0740 pulsar, and it's completely inconsistent with the maximum mass we find when we use this equation of state, which is less than 1 solar mass. So we know that obviously this is not the correct equation of state of neutron star matter, or the matter inside of neutron stars. And so this gives us a way of inferring the equation of state given this astrophysical data. In practice, we want to be a little bit more, we sort of want to be a bit more systematic. And so what we do is we try to establish a probability distribution on candidate equations of state. So over here, this is sort of saying we're trying to establish a probability distribution on candidate equations of state given astrophysical data D, which we can index sort of, these are our different observations. And using Bayes' rule, we can write this in this form. This is sort of just saying the probability of A and B is proportional to the probability of B and A times the probability of A divided by the probability of B, but we're just using this proportionality to ignore the proportionality constant. This is determined by astrophysics. We'll kind of go into that later, but for right now, we're going to focus on this term, which is the prior distribution we place on equations of state. And in our research, we focus on phenomenological models where, for example, what you could do is you could parameterize a functional form. So things like the spectral parameterization or the piecewise polytrope parameterization use this idea. You have essentially a load parameter model that is designed to effectively model a large range of equations of state by using some clever functional form. Another thing I'll be talking about is non-parametric methods, such as the Gaussian process model that we particularly use, essentially trying to drive, to give very agnostic or not trying to build in the structure is maybe the contrast with this type of model. And then, of course, you could also just use a probability distribution on tabulated models from nuclear theory. But the main point here is we're going to be addressing the phenomenological models rather than these tabulated models that have physics directly built into them. We assume that these models don't have physics that are fully driving it, although they might be inspired by the underlying nuclear physics. This is just a quick overview of the types of plots that I might be showing in this, that I'm going to be showing in this presentation, because sometimes they're confusing. So given a prior distribution on equations of state, so given some probability distribution, we can sample from that distribution. And for example, black lines like this in pressure, and this variable rho is the baryon rest mass density, so the rest mass density in baryons. And we can plot this on this plot. And in addition, we can sort of take our distribution and we can compute what the inferred value is for the pressure at any particular density. And by doing that, we can, for example, make a 90% credible interval for the value P at any density rho. And that's what we're plotting here. This is just to say that although this is a 90% credible interval for P of rho, more than 90% of the draws from our equation of state posterior will leave the envelope at some point. So just because a model leaves the envelope does not mean that it's excluded by our inference. This is just sort of a big caveat because these plots tend to be very confusing. And then to go over these labels here and throughout the talk, PSR means that this is just conditioned on heavy pulsar mass measurements. This is kind of a convenient way of characterizing the prior without just using the prior. It gives kind of a clearer picture of what our model is doing when you kind of cut out all of the models that are very heavily ruled out by these heavy pulsar measurements. And Astro here is our entire astrophysical data set that we're conditioning on, which is the heavy pulsar J0348, and then two nicer measurements of mass radii, J0740, J0030, and then two gravitational wave events, 170817 and 190425. It's kind of just number soup. To go into detail on our priors, I'm going to first introduce our Gaussian process regression prior, which was introduced by Phil and Reed in 2018. The idea is essentially you're going to tabulate a draw from this model. So a draw will be this variable phi of pi at all of the pressure points pi, and you're going to be drawing from a multivariate Gaussian distribution. So the idea is that you have a Gaussian process, which is going to induce a Gaussian distribution on the pressure points you want to tabulate at, and this will uniquely determine your equation of state effectively. And so by controlling the parameters for the Gaussian distribution, or the Gaussian process, you might think of it, you can control the shape of the equation of state distribution, which you might imagine is kind of like controlling the shape of this envelope. So you can choose the correlations between different density scales. You can choose the strength of the correlations and the length scale of the correlations by choosing literally the correlations in the covariance matrix between the different pressure values. And in this work, we're using a model agnostic prior, which means that when we condition on nuclear models to kind of build our Gaussian process prior, we're conditioning in a way that's very weak. So we don't want to enforce the behavior of the nuclear models we're conditioning on. Instead, we're trying to just imply the behavior without forcing our models that we draw to fully adhere to it. In contrast, we use three parametric models, or we sort of examine three parametric models. The spectral model, so this is one that was introduced by Lee Lindblom in 2010. This is basically what you're doing is you're going to take this adiabatic exponent and expand it in some basis functions effectively. There's also a piecewise polytrope model, which has been extended to all sorts of different types, but this is a simple one where there's just three segments, and your model is effectively a polytrope with a constant polytropic exponent between each of the separation densities. And then finally, there's the speed of sound model, which is loosely based on Screeve 2018 paper, where the idea is you're going to directly parameterize the speed of sound, and then by doing this, you'll be able to get a distribution on equations of state by sampling in these parameters. And this model is particularly tuned to approach the asymptotic, the PQCD limit of 1/3 in the speed of sound squared. So it's kind of different than these other models. And then as sort of a word of caution, these models are not the most sophisticated models necessarily. but they're designed to be representative of what's used in the astrophysics community. So these are in particular both used by the LIGO collaboration for their analyses of neutron star inference. And on the right, you have the similar plot as to before, except with the spectral model. These are again draws from the spectral model that in this case satisfy some criteria that they have to be not completely ruled out by our astrophysical inference. The data that we use, one of the principles that drives us is that we believe that we can infer the equation of state at different density scales by using different types of astrophysical data. So in this case, this is gravitational wave observation GW 170817, seen by the LIGO Virgo collaboration and their detectors. And near the end of call the in spiral, the tidal deformability of the neutron star starts to be relevant to the gravitational wave waveform. And that sort of leaves an imprint that we can infer, or we can infer the tidal parameters of the merging neutron stars by looking at the gravitational waveform. And on this plot over here, we can kind of see what happens when we just have heavy pulsars versus when we incorporate these gravitational wave measurements. This is kind of a well-known picture that GW 170817 was much more consistent with a soft equation of state. So this green sort of posterior region. And that's kind of a picture of, okay, the 170817 gave us information about the nuclear equation of state kind of in this density region. Versus heavy pulsars, as you can see, are giving us more at the higher densities. Just the existence of heavy pulsars is giving us a lot of information up here at the highest densities. There's also neutron star radii measurements performed by the NICER group, and there's a couple different groups. One in, oh, sorry, is there a question?
Yeah, thank you. So I could see the relative leverage that the heavy pulsars and GW 170817 have on on essentially the density ranges of nuclear matter in the star.
Mm-hmm.
What about those ranges in the fits you just showed on effective polytropic index? Do the pulsars and the heavy pulsars and GW 170817 access different regimes for those?
Yeah, I'll actually get to that later, but that's a very interesting question that we sort of thought about. But yeah, in principle, they should, I would say. You would hope, because these should appear at different density scales. In practice, it's not always as good as we hope. Yeah, I'll cover that a bit more later, though. Thanks for the question. Right, yeah. Essentially, yeah, neutron star radii measurements are another source that we have. There have been two different measurements here, and this one is in particular very interesting because the mass of J0740 was well constrained by Shapiro delay measurements before the mass radius measurement was made. So we actually know the mass of this pulsar to pretty high precision relative to this event, and that gives us this allows us to get a very good constraint on the lower bound on the radius of this star. So that turns out being very helpful in terms of lower bounding or I guess kind of lower bounding how stiff the equation of state has to be, which is in contrast to 170817, which kind of told us that the equation of state should be softer. This measurement obviously tells us that the equation of state should be stiffer at densities that control the radius of these stars. And this is just a GIF. How they get this is very interesting. They use gravitational lensing of these X-rays coming from these X-ray hotspots, and by just using the gravitational lensing alone, they can get a measurement of the compactness. Again, a very interesting place where general relativity is needed in order to interpret this observation. This wouldn't be possible without general relativity, actually. And yeah, just to kind of show the similar plot, when we include these X-ray measurements, we find that the 170817 is no longer dominating here, and we kind of return back up to this point, but slightly more constrained than before. So we've ruled out this upper region that the pulsar is allowed and this lower region that the pulsar is allowed in. We slowly converge to sort of a certain region in the pressure density space by using our data. This is just a brief aside. but I think I might skip it. Suffice to say that selection effects and interpreting gravitational wave data and X-ray pulse profiles, these are all things that we don't fully understand yet. And so when they appear in our analyses, we sort of have to take everything with a grain of salt. And lastly, the poorly characterized population of neutron stars. It turns out that the population of neutron stars appears in our analysis because when we try and compute what's called the likelihood of this astrophysical data given the equation of state, we sort of have to marginalize over all possible neutron star sources. And this depends on neutron star sources depend on the population model. And if we don't know what our population model is, there's uncertainty in this. And this can lead to problems because we don't, what we'd prefer to do is infer the population also in our analysis. But as of right now, we're not doing that. We're just inferring the EOS and using fixed population models. The upshot here is, though, right now, with as few measurements as we have, it's not a huge deal. So the difference in our analysis, kind of two extreme cases, assuming that there's a low astrophysical limit to the neutron star mass, and assuming that there is assuming that the highest neutron star mass is TOV mass limited, is relatively small at this point. It really only affects the maximum mass inference. It doesn't really affect inference of other parameters, such as the radius of a 1.4 solar mass star. So as of right now, the thing we focus on is the EOS prior, because we sort of have an intuition that says that this is probably the thing driving differences between our different analyses the most. And that's kind of one of the morals here, is that, well, in Bayesian inference, if you use different priors, you expect to get different results. So it's not that surprising that when we use the spectral model with a certain prior on parameters and our non-parametric model with our chosen prior, that we get different results when we infer the equation of state. So here we have sort of two different projections of visualizing this data. We can plot these envelopes, which show the inference in P row space at different densities. We can also, as I showed before, kind of look at M max and R 1.4. So this is the maximum TOV mass inferred in this model and the radius of a 1.4 solar mass star induced in this model. And they're different. And one of the things we want to understand is how they're different. And one approach we can take, so to kind of try and give an objective measure, is we know that there is some correlation between this R 1.4 and M max quantity, because causality kind of limits how massive the maximum mass star can be given R 1.4. This is because the pressure at high densities kind of determines the maximum mass, and the pressure at intermediate densities determines this R 1.4. And the relationship between these two pressures must be limited by the fact that the speed of sound is less than the speed of light. So this is kind of a plot of this. There's a line you can kind of draw, although it's a fuzzy line because it depends on the low density behavior of the equation of state. So kind of take this with a grain of salt, which says that this region is excluded because this would require acausal sound speeds. And the picture we kind of get here when we make this plot is that the non-parametric model is sort of running up against this limit, which means that the candidates that the non-parametric model produces are primarily limited by this causality constraint. So there are some correlations in this plot between these two quantities that you can clearly see, but these correlations are being driven by fundamental physics, the knowledge of the fact that the speed of sound must be not acausal. Whereas in the parametric model, in this case, the spectral model, we find that with the prior that we choose, there is this similar correlation, but it's tighter, and it's not, at least it doesn't seem to be driven by this causality criteria. Instead, it seems to be due to something like modeling, the fact that there's such a gap here between the causality line and the edge of the prior, which also drives the edge of the posterior. And so this tighter correlation is sort of what we want to understand. Why does this appear in the spectral model, but not in the non-parametric model? And the answer is that correlations between astrophysical observables, like we saw before, are fundamentally being driven by correlations between density scales in these models. So to kind of explain what's happening in this plot, what we do is we just take our posterior, our envelope plot that we showed before, and we kind of say, well, what if we could constrain the density of the pressure at a certain density? So in this case, twice nuclear saturation density, very precisely. And we can look at how our equation of state distribution responds to this constraint. Basically, we're kind of effectively ruling out models that don't run through this little region and then seeing what their behavior is at different density scales. And the non-parametric model basically returns to the same distribution it had before, about 0.5 times nuclear saturation away on either side from the constraint. Whereas the spectral model, when you enforce the same constraint, is affected over a much longer range of densities. So almost like the entire range of relevant densities for astrophysical neutron stars. And that's saying that there's correlations in these models between different density scales that are causing models, sort of the only models that could predict pressures like this at this density scale were ruled out up here, which is, sort of something that we want to investigate, because it implies that we really don't have as much control maybe over the pressure here as we might have hoped in these models. And we find that this is actually generic. So among the parametric models, when you enforce this constraint, you can get effects at very different density scales. So in the speed of sound model, for example, you get different constraints at different densities. The piecewise polytrope model fares a bit better because these transitions kind of help to break up the correlations at different density scales. They kind of stop information from propagating back and forth. But even then, even up here at 3 to 4 times saturation density, you still get quite a significant impact when you enforce this constraint. Whereas again, in the non-parametric model, you get this behavior that here, when you sort of plot a maximally causal, so the speed of light, our speed of sound approximately equal to the speed of light, and this is the speed of sound about 0.1, which is kind of what we believe is like the minimum speed of sound you need to have for this EOS to be stable in this region. You can see that these are really what are fundamentally driving, at least locally, the behavior of these models. They're really only limited by these causality constraints. And these models, on the other hand, it seems to be completely irrelevant kind of what the causality constraints are in terms of how they respond to this constraint locally. So the way we try to quantify these correlations is with a quantity called the mutual information. Essentially, what we're doing is we're computing how much information do you gain about, for example, PA, from knowing the total distribution, the probability of PA and PB. So this is the pressure at some density A and the pressure at some density B. Rather than just knowing the marginal distributions, if you know the full distributions with all of the correlations between the pressures, you can gain some additional information. And we can also view this as kind of a KL divergence, if you're familiar with this. So this is also, you can imagine, it's kind of averaging over all values of PA. How much information do you gain by, so this distribution PB given PA, how much information do you gain about PB by knowing PA as compared to not knowing PA? This is kind of comparing the information in these two distributions, this distribution versus this distribution. And to kind of come full circle, changing this distribution, so for example, by adding a Mach measurement of the pressure, is equivalent to kind of tightening this distribution, and that changes this whole quantity. And there are some caveats, though. In general, this quantity scales with the uncertainty in the marginal distributions. This is just kind of a feature of quantities like entropy. So the goal is we want to try and keep this mutual information small, even when we have large entropy in the marginal distributions. So in general, that means just having a wide distribution at each of these different densities. And essentially what we find is that we succeed. So the non-parametric model does significantly better than the parametric models. So it has a smaller mutual information, which means that the pressure at any particular density is less informed by its neighbors. So this is kind of a generalization to 5 different pressures. So this is just the definition for 2, but you can see how you can extend it to multiple pressures fairly easily. The point is that the non-parametric model has a lower mutual information while simultaneously having wider marginal distribution. So it's actually kind of winning on both counts. It has more entropy in the marginal distributions, but the mutual information shared between different pressure values is actually smaller. And the spectral model, because of its extremely long correlation length, driven fundamentally by the fact that it's so smooth, there's so much smoothness enforced in this model that we find that it actually suffers from sort of the worst correlations in some sense. It has the longest correlation length scale of any of the models we examine. And again, as you can kind of expect, the piecewise polytrope with its sharp cuts is actually doing somewhat better in this metric because it has shorter correlation lengths. And then sort of finally, the last thing we did was kind of check what would happen if you tried an experiment like this, but with astrophysical data rather than kind of measuring so we're having mock astrophysical data rather than mock microscopic data. And we inject an EOS that we kind of expect the spectral model to fail to recover because it lies outside of the 90% credible region that we saw before in this Mmax R1.4 plane. And what you can see is when you infer it with gravitational wave events or with electromagnetic events, well, when you infer it with electromagnetic events, you can determine the mass fairly well. We have some very good mass measurements of heavy pulsars that have relatively high precision compared to our other measurements. And because of this correlation, when you measure Mmax well, you end up inferring the incorrect value of the radius of a 1.4 solar mass star. So that's why you can kind of see that this red line, which is the true value, is not being found by this spectral model, which is sort of what we'd expect, because if your quantities are correlated and you measure one very well, you measure the other very well, even if you're measuring it incorrectly in this case. And this sort of gives a sense of tension that might arise if you're using different types of observations to measure different density scales. Then you'll get the same effect. It'll end up being, you might be inferring things about a different density scale that are not actually correctly inferred. They're sort of, you're overgeneralizing because of the model. And on the flip side, you can try this with injecting a model that injecting a candidate that the spectral model produces that the non-parametric model looks like it should fail to recover. And it turns out you don't get the same behavior. So while the non-parametric model converges slowly to the correct value, even though, for example, in this case, this red mark started outside of the 90% credible region, eventually it ends up inside after we include all of this mock astrophysical data, which indicates that you're not getting a bias. You might be slowly converging. It might take a lot of data, but that's not exactly the concern. We wanted our model to be agnostic. That was the target from the beginning. One question you can ask is, well, why don't you just modify the parametric distributions or the parametric models to get more flexibility? So for example, you could take the spectral model and add more terms. It turns out that this is actually quite difficult. For the spectral model, if you keep adding more terms, you'll be adding higher and higher exponents here, which will lead to more and more kind of oscillations, which, in certain cases might be what you hope for. So in certain cases, but the problem is the model is kind of limited because in general, you have to fine tune these parameters in order to get the values of this adiabatic exponent to be reasonable. So each time you add a term, you have to refine tune the model, which is kind of annoying. A thing you could try is just reweighting the prior distribution that you're using on parameters. So changing the prior distribution and seeing if you can eliminate the correlation in this way. So this is what we tried to start. And so, for example, we can reweight all of the parameter distributions, all of these prior distributions on parameters. And it turns out that it doesn't actually change the correlation that much. So we can get a change to the distribution along the axis of the correlation, but the functional form itself of the model is what's driving this correlation line here. So you can't get much of an improvement in this direction. So sort of in the direction we want to improve in by just broadening the parameter distributions. And this is pretty generic, we find, which is kind of a challenge. And one way to view this is Well, with the current data, it seems like we're really only inferring a couple of parameters very well. So only this gamma 0, which you can kind of, it's related to maybe a polytropic constant, and gamma 1, which is kind of related to a polytropic exponent. That's saying that this parametric model, the spectral model right now, is maybe behaving more like a 2-parameter model than a 4-parameter model like you'd hope. And going back even in the paper where Jocelyn Reed introduced the piecewise polytrope model, it's noted that the model will really only be good as long as the number of observations you have is smaller than the number of parameters in the model. So this is kind of a warning maybe, because if you thought you had a high parameter model, even if you thought you had 10 parameters or something, you kind of have to check to make sure that all of your model parameters are active, because you might actually have a much lower dimensional model, which could be causing these types of problems in your analysis. So the answer is, why not just modify the parametric models to get more flexibility? They're fine-tuned in general. So the spectral model and the speed of sound model sort of have some fine-tuning that go into them. Or you might need to overhaul the models themselves in order to get the improvements. So you might need sort of larger scale improvements. And this is definitely already being done. There are lots of examples of better piecewise polytrope models being introduced with smooth transitions or with moving transitions. So you infer the transitions rather than just fixing them. But again, the extensions are non-trivial. And so maybe a lesson here is that it's good to understand the limitations of each of your models when you're using it, because odds are if you have a low dimensional model, these limitations will appear sort of generically. Again, I want to emphasize that not all correlations are bad. Physical theories have correlations by design. So in F equals ma, F and A are correlated, and that's the whole point. But the goal with this type of modeling, when we're trying to do astrophysical inference, is to have control over these correlations, because these correlations really drive the amount of flexibility, or the flexibility in the choice of correlations drives the flexibility in the type of prior distribution we can place on models. And that's something that we really want to be able to have the maximum amount of flexibility. We want to be able to choose any prior that we want. And we find with the Gaussian process that this is actually, this is pretty easy by changing the correlations. So this is a plot from Reed and Phil and Dan Holtz's paper from 2019. You can take something like a model agnostic prior, which is the one we used here, where you loosely tie all of your draws to the overall set of candidates that you've chosen, or you can require them to stick very closely to this distribution. And then you'll get a very different prior, and you can do a different analysis. But that's a choice you get to make by using this model. Actually in the Maryland group's analysis of nicer data, they actually use a Gaussian process that looks much more like this, and it targets a different objective in general than using a maximally agnostic model. You're building in more information from these nuclear models into this theory. And finally, eventually, you'd hope that you'd infer these correlations just like any other parameters in the model, but obviously that will require much more astrophysical data in order to get meaningful constraints on these types of parameters. Although you could also fold in nuclear information like nuclear theory and nuclear experiment into these types of predictions, which is something we're very curious about. In conclusion, phenomenological models of the nuclear equation of state are very prone to having correlations built into them, especially if they're low dimensional. And these correlations are due to the functional form of the EOS. The non-parametric model that we use, the Gaussian process model, gives you the flexibility to kind of avoid having very strong correlations, but it doesn't guarantee that you won't have strong correlations. It just gives you the flexibility to choose the correlations. And these correlations are sort of both astrophysical. They appear both in our inference of astrophysical quantities, and they also appear in our inference of the properties of dense matter. So there's kind of this correlation, and it's directly related to the fact that we're using general relativity to probe nuclear matter and nuclear matter to probe astrophysics. So thanks everybody for, I'm happy to take any questions.
Yeah, thanks a lot, Isaac, for this very nice talk. So do we have any questions? Okay, I can see Ermal.
Hi, well, thank you for the great talk, and hopefully you can hear me. My voice might be low. My question is more philosophical in nature. So great work. I really liked your talk, but I was wondering why you chose a parametric or parametric models which are generic rather than pick equations which are built for microphysics. There are decades of work where people use in nuclear interactions, we build from the ground up equations of state. So why not use that? Because the correlations that are there have some physical meaning to start with, rather than a functional form that was picked to fit some data. So why go this route, not the other route?
Yeah, so that's a good question. I think this is intentional. So the fact that we're using a phenomenological model rather than these models that are driven by fundamental physics is because really this is what's used in astrophysical analyses. And this is one of our primary concerns. I think in practice, we would prefer that our models were more driven by fundamental physics. And that's something we want to be able to get at with this Gaussian process, is be able to build this nuclear information into the model without being limited by the form of the model. So I think that's absolutely right. This is, in general, these phenomenological models, we do not think are really the correct approach in the long term. We think probably that if you want maximally agnostic or very targeted models, you should prefer to use something where you have the choice to make that kind of thing ahead of time. So, but it would be interesting to compare the Gaussian process, the results you get with the maximally agnostic Gaussian process, to much more targeted nuclear models. I do think that would be an interesting analysis to do.
Okay, thank you. Next question is from Zilu Lin.
Okay, yeah, thank you so much for this talk. Very interesting. So my question is that, so we know that there are some equation of state that can describe, that include the phase transition. And if there are some equation of state with the phase transition, you will see that, for example, the energy density as a function of the density, it will be discontinuous. Or if you are plotting the speed of the sound as a function of the density, that will also, if it is in the first order phase transition, then it is discontinuous. Mm-hmm. So I'm just wondering if this Gaussian process can describe such kind of the discontinuity.
Yeah, so in general, I actually have a backup slide about this. So this is definitely something that we know that these parametric models struggle to pick up on, but the Gaussian process model can not exactly produce candidates, but it can mimic candidates that look like this. So if maybe I can go back to the beginning. Actually, this is maybe a better example. Because so in this plot, we're showing P versus rho. Obviously, P versus rho is not the whole story, kind of like you said, because the energy density may be discontinuous. But if you plot the energy density versus pressure, there are certain equations of state which have, well, you can imagine a very long region of P constant versus energy density increasing, and this sort of we believe the Gaussian process can at least approximate candidates that look like first order phase transitions. We know that we have very rapid variation in the speed of sound. So the speed of sound changes can change very rapidly over small length scales. And we can actually choose the hyperparameters, so the parameters for this covariance kernel, to kind of encourage that to happen. By building in very short correlation lengths, you can encourage the model to produce candidates that have, for example, a very steep drop in the speed of sound, which would be characteristic of a phase transition. And so, yeah, we think that the model is able to do it, but we want to make sure that in practice it's able to do it. This is kind of a question of how much data do you have? How many samples do you have? Can you effectively resolve these phase transitions with the correlation links we're using? But generically, we expect it to be able to do it, at least, in the limit.
Okay. Yeah. So so if I understand correctly, probably if we want to reproduce this kind of the discontinuous equation of state, then maybe we need to somehow decrease this kind of the interdensity correlation, because maybe we want maybe the density correlation length to be very, very small, so that we may somehow reproduce this kind of the sharp change of
yes.
Okay.
Exactly.
Okay, I see. Okay, thank you. Mm-hmm.
Mm-hmm. Yeah.
Thanks. There is one more question, at least from Dake.
Yeah, thanks for the talk. My first question is, so one of your claim is that the Gaussian process can help you control the correlations among different densities, but I'm assuming you are using a stationary sort of covariance matrix in the Gaussian process. Is that correct?
Yeah. So in this case, for the Gaussian process model, what we use is actually we take several different choices of hyperparameters, so of basically of different covariance kernels. They're parameterized by the correlation length and the correlation strength. We use a fairly simple model for the form of the correlations. It's basically just like a Gaussian. And so what we do is we choose many different combinations of correlation length and correlation strengths. And we kind of clump all of these models together. So we can generate a bunch of draws with each of these different Gaussian processes, and then we can just add them all together. And that includes conditioning on nuclear models. So some of our models are conditioned on just hadronic, some are conditioned on hyperonic, and some are conditioned on hybrid quark hadronic models. And we just, to make this model agnostic prior, what we do is we just take all of these things and then put them together. So we just end up with something like 2.5 million draws of varying origins of different different correlation.
Right. So, but by combining all these kernels with different lines, you're still getting stationary kernels, right? So basically, you're assuming, say, if there's a correlation between, I don't know, 0.5 and 1 times saturation density, then there will be the same amount of correlations between 1 and 1 and 1.5, and 2 and 2.5, 3 and 3.5.
Yeah, yeah. So yeah, that's true, but we draw in log pressure. So it's that's correct. But yeah, it's stationary in log. Yeah.
Sure, but yeah. So yeah, then one immediate question following the last one is, when there's a phase transition, really, whether you're doing log p, I mean that will introduce a very particular tiny length scale that is unique to the transition density, and
yeah,
I really don't see how Gaussian process can capture that. And also, I really don't see why it's really, what's the physical motivation behind assuming that there will be a stationary correlations either in P or log P or E in log E. Do you have any thought on that?
So I think, yeah, that's a good point. I think right now these are like limitations of our model, that the fact that it's stationary. In principle, we'd want to have a much wider choice of kernels, but where that are not stationary. And again, we'd want to be able to choose these kernels in a way that's motivated by physics. So you'd want to be inferring the kernel, from the data itself. But right now, I think, yeah, these stand as limitations of the model. There probably is no good physical reason why the equation of state should have a stationary distribution, or the equation of state model should have a stationary kernel. That's a good point.
Okay, if I can ask a second question, if time allows. Okay,
sure.
Right, so when you make the comparison between the Gaussian process, say, and the piecewise polytrope, well, if I remember correctly, you only use 3 pieces, right?
Yeah.
And so how many points is in log P do you sample for the Gaussian process?
700. It's a ton. So yeah, this is not a,
so that's not a really fair comparison, right?
Exactly. No, I think, yes, that's true. It's not a fair comparison. But the point here was kind of to try and look at the models that are most commonly used in astrophysics. And so, this is still considered, the standard in much of the analysis that goes on. But like you said, of course, it has 4 parameters. How is it possibly going to match the model freedom of the Gaussian process that has something like 700 parameters, right? If you look at it in that picture, then, but even then, there are extensions of piecewise polytrope that may include 6 or 8 or 10 parameters. We don't expect these conclusions to completely disappear. They'll get more and more hidden because the models are better, certainly, but they're still going to be present. These problems are still going to be present. You still have to be aware of them, that these correlations will appear. And the point here is kind of, when you make a new model, you probably want to characterize it. It's just super easy to see the correlations in a model like the 4-parameter piecewise polytrope without moving transitions. It's just, they just appear.
Yeah, thank you.
So then in the meantime, there was another question that appeared in the chat from Emanuel Chimansky, who is saying, nice work looking at the equation of state you sampled from your GP, the dark lines with the blue cloud. It seems like the dp over d rho is always positive for every row. How did you do that? Is it related to the kernel you choose for the training?
So yeah, the dp by d rho being positive is actually because we sample in this variable phi. So by sampling in this variable phi, it has this kind of crazy expression over here, but you can check that if you can write down an equation of state, or if you can compute this value phi for a particular equation of state, that implies that the speed of sound is between 0, or the speed of sound squared is between 0 and 1 everywhere for every value of pi. So by sampling in this parameter, we guarantee that the equations of state we draw are stable and causal. So in that case, this ends up being enough for this model to guarantee that dp by d rho is always positive. This kind of stability criteria.
Okay, hope that answered. And there's one more question from Jianqi Zhao, so please go ahead.
Hi, Isaac. I have a question regarding this slide when you propose this parametric form, that log of this 1 over, so just this form, this slide 8.
Oh yeah. Mm-hmm.
This form you take, can I consider it as a parametric form as well? If you change another form, is it like changing from to spectra as well? Because you have tons of freedom to choose here.
So yeah, this is in a sense a parametric form, or a functional form for the equation of state. I think the point is, though, that when you build enough parameters into your model, your parameters are not responsible for large density scales. So in a model like the piecewise polytrope, you can see explicitly what density scales per certain parameters are responsible for, right? They're responsible for the scale of densities kind of between which your transitions happen. But this is not going to be subject to the same problems for a couple of reasons. This is kind of better than the piecewise polytrope. You can actually, I mean, you can explicitly start to add parameters to your piecewise polytrope. You can just tabulate it at 700 points, and you're still going to have problems because there's no correlations naturally between the different adiabatic indices, or you can imagine that's kind of the same as correlations between the sound speeds. So the benefit that the Gaussian process has is, one, it has a ton more points. That does help. It'll help any model. But two, it has correlations built in between density scales that you can control. So these are the two kind of key ingredients that, if you wanted to generalize for example, the piecewise polytrope model, these would be approaches you'd want to kind of to go at if you were trying to get the same type of model freedom that you get from the Gaussian process.
Yeah, sure. That part I do understand, but you call this non-parametric, this non-parametric is bothering me because you really take a
Yeah, so this is an unfortunate naming convention, I think. I think maybe one way to think about it is that for a non-parametric model, you would hope that the form of the parametric model doesn't matter that much. And this is something that obviously you'd have to check.
Okay.
But yeah, no, I mean, I agree. I think non-parametric is a poor naming convention for the long run, because non-parametric really just means many more parameters than
Cool.
a parametric model, right? I don't. It's an unfortunate name.
Okay, thank you.
Okay, thanks. So do we have any other questions? I don't see any at the moment. So thanks again, Isaac, for the very nice
Yeah.
talk and for answering all the questions. Thanks everybody for the questions as well.